Hello everyone, and welcome back to Electronics Prepper, the channel where we try to learn as much as possible about electronics to become more self-reliant with technology and prepare for the future. Today I will show you a device that I designed, built and used for the last few days to measure litiu accumulator real capacity. This is a problem that we have whenever we buy litiu accumulators from the market, from questionable vendors, or when we take second-hand accumulators that we don't know anymore in what shape they are, how much capacity do they still have left, or in general when we want to test the real capacity of litiu accumulator. Now, there are some devices out there on the market that supposedly do something to assess the total capacity of an accumulator. However, as far as I know, they're not really discharging completely that accumulator and, performing all the necessary measurements and calculations. They are, I believe, just discharging the accumulator for a few seconds, and they calculate the voltage drop and something like that. I'm not sure how they work. There are also some chargers that are able to measure how much energy they put inside the accumulator as they charge that accumulator to the maximum. Those numbers are pretty close. I would say they are pretty close to reality, but they're not quite 100% because the process of charging an accumulator is still different than the process of discharging the accumulator. We know very clearly that when we discharge the accumulator, the higher the current that we're drawing, the less energy we will be able to obtain from that accumulator, because overall we will have bigger voltage drop and the accumulator will discharge faster. Okay, so the only good method is if we have a device that is able to discharge a fully charged accumulator up until a certain threshold, or I should say perhaps down until the voltage gets to a certain threshold, which in my opinion needs to be 3 volts. Some people say it can be even lower, 2.7, 2.5. I would say 3 volts for lithium-ion litiu polymer. And meanwhile, measuring the current, measuring the voltage, and doing the necessary calculations. Now, there are some devices like this electronic load that you can find on Amazon, eBay, or in other shops that are pretty cheap, but they're still not quite cheap enough, in my opinion, to be worth buying just for the sake of testing lithium-ion accumulators or lithium polymer accumulators. I would say we can build something with an Arduino that is considerably cheaper and with which we can actually test 2 accumulators in parallel. So this is what I will show you in this video in the following minutes. But first of all, please allow me to give you some good news and to thank the sponsor of this video, which is PCBWay. If you need help creating your PCBs, maybe even assembling them with components, or perhaps you're building a device that needs a case and you would like that 3D printed or CNC machined, then you can definitely rely on the quality services of PCBWay. To make things even better, since we're moving towards Christmas time, they are currently offering Christmas big sales, discounts up until the end of this year. You might find you can benefit from 50% discounts on ordered PCBs, 3D printed objects or CNC machined ones, free Christmas coupons based on your order size, and they even have a lucky draw where you could win some goodies by just clicking the virtual boxes on the screen. Go check out what they have to offer, the links are in the description below. Thank you PCBWay for sponsoring this video. And now let's get started with this device that I would like to show you. So let me quickly show you the finished device in a plastic case, in a 3D printed plastic case, an almost finished device. I just needed to 3D print the cover and assemble everything together. As we can see, we have an Arduino Uno at the center of attention. Honestly, I'm not a fan of Arduinos in general. I kind of avoid them. But sometimes it's impossible, like when we're trying to build, a measurement device. We need to have some form of display, and it's nowadays the easiest solution is to just take a microcontroller board and any LCD display that is cheap, and just connect them together, write some software. So in such cases, I do tend to go towards a microcontroller board, not particularly Arduino. However, this time a viewer of my other channel has donated to me one Arduino set, an original Arduino, not that it matters, and a whole bunch of other accessories. So because I'm not a fan of Arduino, I thought, okay, I'm gonna use this Arduino here in this project. I also have power from an X phone charger because it's good enough for this project. The whole device will only suck about 50 milliamps or so, very low current. So even a half an amp old phone charger that gives 5 volts, that's the only requirement, it should give 5 volts on the output, will be good enough. So I have reused such an old phone charger. On the left we also see an LCD 1602 screen. These are pretty cheap, $2 or $3, something like that. And on the bottom we see a couple of perforated boards with some components on them, and this is the custom circuit that we need to build for this project, and the one that I will show you in a moment. On the upper side we see a couple of radiators with one each with one power transistor. That's actually a Darlington pair, but it's one of those Darlingtons inside a case, inside a capsule that resembles a power transistor, because we will need to dissipate some power while we are discharging the accumulators that we want to test. So this is pretty much what this device is made of. And this is the schematic. We have 2 channels because, like I said, we will make this to be able to test 2 accumulators in parallel. This is because we have enough digital and analogic inputs on the Arduino. Of course, we could build this with only 1 channel, but it doesn't make sense since we have enough resources to test 2 accumulators at once, so have 2 different channels. But I will only explain 1 channel, the other one is basically identical. For both channels I chose an MicroCap 6004, it's a microchip quad op-amp, rail-to-rail input-output. So this is basically the only thing that differs. We're not using different op-amps for each channel, but rather one chip that has all 4 of them inside. Now, my idea was to create an air-to-air DUC with 3 pins, so basically a 3-bit DUC, to generate a certain voltage. Have that voltage applied to a non-inverting input of an op-amp that basically acts like a comparator. That op-amp would command Darlington pair transistor, power transistor, which will be connected to the litiu accumulator. So the current that will come out of the accumulator will flow through this Darlington pair, and this Darlington pair will be opened and closed by the op-amp based on how much current we want to draw from the accumulator. And this current is measured through two resistors here, 0.1 ohm each. I said that I want to have anything between 0 and 5 amps of current. I don't think I will ever test any accumulators with more than 5 amps. So yeah, 5 amps should be enough. So I chose a shunt resistor of 0.2 ohms made from two 0.1 ohms each and 5 watts each. At 5 amps, this gives us a 1 volt voltage drop across them, okay? And this voltage is sensed through the inverting input of this op-amp that again acts like a comparator. So when the voltage here is lower than what we have on the other input, on the reference input, let's call it like that, then this op-amp will turn on the Darlington pair transistor, which will draw more current from the accumulator. And when he has drawn enough current that we have here the voltage that we are feeding through the reference, then the op-amp will shut down the transistor so that no more current flows through him, and everything will stabilize over there, okay? In order to control this digitally, like I said, I thought of building an air-to-air DAC, basically the cheapest, simplest DAC that you can have. By the way, if you don't know what DAC means, it means a digital to analogic converter. And I'm not going to show you in great details how this works. You can just search on Google air-to-air DAC and you will find plenty of resources, even a Wikipedia page about this topic with mathematical calculations and all the necessary explanations of how such a DAC works, okay? Now, the problem is with a regular air-to-air DAC, you get equal values, equal voltages between each digital number. Since the Arduino is the Arduino digital outputs are basically offering about 5 volts, this DAC would go up to 5 volts, almost up to 5 volts from 0. And the step voltage would be 5 divided by 2 to the power of 3, which is 8. So about 625 millivolts. Now, if we apply 625 millivolts across 0.2 ohm resistors, we get 3.125 amps. No, wait, sorry. I think I've done stake. So the smallest value that we can have is right. Okay, so first of all, since we want 5 amps maximum, therefore on the shunt resistor we can have 1 volt maximum. Having an up to 5 volts voltage from our DAC is too big. Of course, we can step that voltage down by using a voltage divider, which is something that I've done here with the R3, R4 and R9. However, let's say that we are dividing 5 to 5 in order to get 1 volt maximum for the maximum value. Therefore, each step would be 0.6 volts divided by 5, which is 125 millivolts. However, 125 millivolts applied across a 0.2 ohm resistor shunt equals 625 milliamps, and we could just make 625 milliamp steps furthermore, equally spaced apart. Personally, I did not like this. I wanted some smaller values that are closer to 0, and then some more spread out values that go up until almost 5 amps or so. So I couldn't create a regular air-to-air duct, you know, like they show us on, you know, other websites, and with equal to air value resistors and equal air value resistors. No, mine had to be different. So I used a slightly more complicated resistor ladder, as it's it's called as well. And yeah, I cannot say that I have calculated this in any way, because I don't even know how I could have calculated. So what I did to figure what these values must be is basically go into MicroCap and have a simulation. Just create the circuit and have a simulation, and then change the values up until I had something that I liked. And MicroCap, in case you did not know, it's a free software that you can download from the internet. He also has something called animated things, animated switches, animated LEDs, and other things. So you can add an animated CPDT switch, single pole double throw, and what animated means is that you can double click him and he will change his configuration, you know, and you can do this in real time while you are simulating your circuit, and he will give you a result. So basically this would be a very easy way to do this. So I have set up here a circuit with a 5 volt power supply, 3 switches that are equivalent to 3 digital outputs on my Arduino, and a bunch of components that again, I started from the air-to-air configuration, standard configuration, and then I kept changing these until I had my desired values. So here in MicroCap you can even simulate more complex expressions, so I was able to just calculate what would be the actual final current, at least theoretical, that will be sucked from the litiu accumulator, you know, by calculating the output voltage here and dividing that by 0.2 ohms. And that will give us a value between 0 and 5 amps. And with this particular configuration of resistors plus 2 diodes, because I discovered that I need to have the most significant bit work differently when it's 0 logic than when it's 1 logic. So I placed some Schottky diodes here that change the flow of current, so that when this pin is 0 logic, this 1.8K resistor will be working, and when this pin is 1 logic, this other 5.6K resistor will be, you know, functioning and dragging things up, and will give us a different result, basically. Okay. So so let's start from the beginning. If we have 3 bits, then we have 8 total values, including 0. So the first value after 0 will be when the least significant bit is 1, of course, and the others are 0. So this should give us about 300 milliamps of current. Then the next value is going to be about 700 milliamps. Then the next value is going to be almost 1 amp. Then the next one will be about 2.8 amps. The next one 3.4. The next one 4.2. And the final value, when all of these bits will be 1 logic, should give us 4.8 amps. Now this is theoretical. In practice, we are having slightly different values due to the fact that, of course, my resistors were not perfect. They had tolerance, you know. The Arduino is not really giving 5 volts for 1 logic on the output and 0 volts for 0 logic. It's giving something less than 5 and more than 0. Not by much, but it's still something. Anyway, but this is basically how I created this custom resistor ladder that satisfies my needs precisely. Okay, and I would say that these values are pretty good to go from 300 milliamps theoretical to almost 5 amps is pretty nice. Okay, so this is how we generate this, let's call it reference voltage to feed this comparator that would in turn generate that particular current from our litiu accumulator. Now, what we need to do is to basically measure the voltage across the accumulator and the current and perform some calculations. So this is why we are taking with this 1.3K resistor. It could be larger, it doesn't have to be, I just chose randomly 1.3K. We are taking the positive terminal of the accumulator and feeding that directly into one of the ADC inputs of the Arduino, and we are also having a protection diode from that analogic pin towards the plus 5 volts that would normally be closed, but this diode would start to conduct if anything happens on the input and we are providing more than 5 volts so that we don't burn the Arduino input. Okay, this is also why we need this current limiting resistor. So by doing this, we know what the voltage across the accumulator is. We also need the current. The current basically is this voltage across the shunt resistor. However, even in the worst case scenario, when we have 5 amps, we would only have 1 volt here across this resistor. We could feed this directly to another ADC from the Arduino. However, the Arduino is expecting a 0 to 5 volt analogic voltage on the ADC inputs. If we give him less, he will measure that voltage, but we won't have, you know, a proper resolution. So we want to have an as precise measurement as possible. So it makes sense that we just take this voltage and amplify by a factor of 5 to, you know, have more resolution and therefore more precision. And this is what we are doing with the second op-amp. It's a standard non-inverting amplifier with a factor of almost 5, a theoretical factor of 4.9, and we are feeding this directly to another ADC, A1 here. We don't need to protect this input in any way, because since this op-amp is powered from the same 5 volts like the Arduino, it's gonna be impossible to give on the output anything more than 5 volts. So the op-amp in this case will provide us with the necessary protection for the ADC inputs. Okay, and this is pretty much it in terms of electronics. This is everything that we needed to do with our litiu accumulator to do the measurement. We also have here a 100 microfarad capacitor in parallel with the accumulator. It doesn't need to be 100 microfarad. I would say, I don't know, anything above 10 microfarads is good enough. This might appear a bit weird, but in my tests, when I was testing this with a lab power supply, I had cables of almost 1 meter from the power supply to this device. When I was trying to draw more higher currents, that cable appeared to have, I don't know why, but that cable appeared to have too big inductance and would start to function like a coil, like an inductor. And yeah, I started having problems. I started having big spikes of voltage here, which needless to say were not good at all. Yeah, and the only way I could fix this is if I place this capacitor here in parallel with the input. Okay, in terms of other things that we are doing on the hardware level, I chose an LCD 1602 screen. That LCD needs 6 pins from him connected to the Arduino. I chose digital 8 through digital 13 Arduino pins to be connected to this LCD like this. Okay, we have the enable pin on digital 12, the RS pin on digital 13, and digital 4, 5, 6, 7 from the LCD screen connected to 11, 10, 9, 8, okay, from the Arduino. We also need a 1.8K, or at least that was the good value for me, resistor from VO from the LCD screen to the ground, because we need to set the contrast of the LCD screen. For me, 1.8K was good enough. You might want to play with this value to see what screen contrast works better for you. And you also need to tie the read-write pin of the LCD screen to the ground. On top of that, the LCD screen also has backlight that has 2 different pins, a cathode and an anode. The cathode needs to be connected to the ground. The anode, on the other hand, be careful, while the LCD screen is powered from 5 volts, the anode must be connected to the 3.3 volt output of the Arduino Uno. So the backlight does not power from 5 volts, but from 3.3 volts. Okay, this is something to take into consideration. And on top of that, we want to control our device with 2 buttons. We need at least 2 buttons to be able to control him. Okay, so we still have 2 digital pins free, 6, the digital 6 and digital 7 GPIO. So I have used them for some push buttons and to perform that debouncing thing. You know, I have placed some capacitors in parallel. They don't need to be 220 nano. They can be anything, I would say, from 100 nano upwards or something like that. I mean, don't put too large capacitors, of course, but anything around 100 nano, 200, 400 nano should be good enough. These pins will be in software configured as pull-up pins, so pins that will have a pull-up resistor inside the Arduino. So normally they will stay on 1 logic, and when we press the buttons, they will go down to 0 logic. Okay, 1 button I called him action, and 1 button select. So with the select button, we will basically be selecting different things on the screen, and with the action button, we will be taking various actions on the screen. And this is why they are called like this. And And this is almost it. I also had, so in order to power this, like I showed you earlier, I chose an old phone charger that gave me slightly more than 5 volts. And I would recommend you do the same. Choose a power supply that gives you slightly more than 5 volts. There are some power supplies that give you slightly less than 5 volts, and yeah, I would say choose to go slightly higher than that. For me, this power supply gave me 5.15 volts measured directly, but with a bit too big ripple and some high frequency spikes. Those would not be good for the Arduino, for the accuracy of the measurements. The Arduino himself doesn't care, but you know, when it comes to taking measurements with an analogic digital converter, any fluctuation in the power supply voltage can cause a fluctuation in the values that the ADC reads. So in order to, you know, smooth that voltage more, I chose a 100 microhenry inductor in parallel with I chose an LC filter, okay, and I'm powering everything from this LC filter. 100 microhenry inductor with a 10 microfarad capacitor seems to be good enough to smooth the voltage coming from that old phone charger. And this is pretty much it when it comes to the electronic side, the hardware side. I had quite a bit of work to do on the software side. I am not going to go into great details about what I'm doing here. At least half of this source code, which has about, by the way, 500 and something lines of C code, at least half of this source code is concerned with with the user interface, with you know, responding to buttons the way you're supposed to, displaying things on the screen the way you're supposed to, and only half of this, or perhaps even less than half of the source code, is actually concerned with you know, reading ADC values and calculating currents, calculating things. That's a much smaller portion. I'm going to put up on Patreon for all the paid members. I'm going to put all the project files for this project, the schematics, the source code, everything, so that you can create this yourself if you want to. Now, you will need to perform some small changes to the source code. Here in the very beginning, you see some comments, change here for your needs. You will need to, first of all, take your most precise voltmeter and measure the voltage here after this LC filter, the voltage that will eventually go to the Arduino, to the op-amps and the rest of the circuit, and write this voltage in millivolts here in this constant power source voltage here. Because, like I said, the Arduino takes, unless we give him an external voltage reference, which in this case I haven't, the Arduino will use the power supply voltage for the analogic digital converter for the maximum value that he can read. And so we cannot just simply blindly consider that 5 volts sharp, when in reality we will not be having 5 volts sharp. If we care about, you know, the accuracy of our readings, we need to set here the correct power source voltage. In my case, it was 5.078 volts, so 5078 millivolts. So this is what you need to write in here. Before you place every component on the board, you also need to measure Ru17, Ru18 here on this amplifier on the first channel for this for these shunt resistors, and also root 30 and root 32. And you're gonna need to calculate, based on the real values that you measure, calculate the amplification factor of these amplifiers and write them here. Channel 1 current amp factor and channel 2 current amp factor. Normally they should be 4.9, but again, they will never be 4.9 sharp. In my case, for the first channel I had 4.922, for the second channel I had 4.865, because I used just regular 5% tolerance resistors, okay? So this will give you a slightly different value. And again, in order to calculate things as correct as possible, it is best if you take these measurements and place them here. And that's it. These are the only three things that you need to change in the source code. Other than that, the source code just works, okay? And does quite a few things. So this is pretty much it. I will go to the workbench now to show you exactly how the user interface works, because you might not figure that you know, all by yourself. Again, we only have two buttons here to do everything. We don't need to do a lot, but still, if you choose to download these files and build this device for yourself, you don't want to just guess how that works, because that can be annoying. In the next videos that will come, I will show you some more concrete results of various accumulators that I've tested, and I will talk a little bit more about, you know, my experience buying very cheap accumulators from the market and why I needed this device. I needed to create this device in the first place. Okay, so now let's go to the workbench and let me show you quickly how this device works. Right. So, this is the finished device, okay? I chose a blue LCD screen because I hate blue LCD screens, so I want to just use them, all of them, slowly on various projects. I also chose, so this is a 220 volt cable. I chose this cassette tape type of power cable because you can find these connectors on the market, and you can also find these kinds of power cables pretty easily. I believe most of you already have something like this. Anyway, this was just my choice. Also for the output connectors, I chose just M4 screws with nuts, because I find them easy to just clip crocodile cables, you know. Anyhow, when you power up this device, and in parallel I will also power one of my lab power supplies, so that I can give you a bit of an example, a live working example. You will find that this device starts with these two lines here. The first line is for the first channel, the second line is for the second channel, okay? And the device shows you three things at once. An icon here, which can be this play triangle, the two vertical bars that are equivalent to the pause button, and a checkbox I will show you towards the end. This voltage here represents the threshold voltage, meaning how low do we allow the accumulator voltage to drop. For any serious test, you need to first charge your accumulators all the way to the maximum, which is typically 4.2 volts, and then they will discharge down to this level, okay? and a current that you are trying to get from the accumulator. They start at 1.1 amps and 3 volts. However, with the select button, which in my case is this one down, we can start to change things. The select button will cause a cursor to blink on the screen, and we can move this cursor in various places so that we can, you know, set up that particular aspect. So when we want to change the threshold voltage, we press the select button until we get to the threshold voltage, and then the action button, which is this one here up, to, you know, choose a different value. The threshold can be set between 3 and 4.2 volts in 0.1 volt increments. Honestly, I don't know why you would choose any other value besides 3, but anyway, it's something that you can set if you want to. Then by clicking another time the select button, we go to the current, and we can go through the various preset values that we have. So I showed you in the MicroCap simulation the approximate theoretical values. In reality, due to all of these physical factors that come into play, the difference in resistors, the difference in output voltages from the Arduino, in reality we have slightly different values. We have the smallest current, 420 milliamps, next one is 810 milliamps, then 1.1 amp, 2.7, 3.3, 4, and 4.6 amps maximum current. Okay, for me, I would say these are enough, and these are nice values to have from a relatively small current that's less than half an amp all the way to almost 5 amps. Now, when you change the current, because the device thinks that you are now ready to, you know, start that particular channel, when you press select, he will jump back to the play button for that particular line in which you have changed the current. If you do not change the current and you press select once more, the cursor will move to the second channel and will go through the other settings of the second channel. And at the end, if you press select again, the cursor will disappear completely. So now you cannot set anything anymore. You cannot perform any action anymore. Okay. So let me connect my power supply. Let me adjust the power supply first. 4 point something volts. I'm going to just make a test with the first channel. The second channel is identical, basically. Okay. So I have connected my power supply and I'm now ready to start the test. So I will go with my cursor on the play button and I will click the action button. Now the cursor has transformed into a pause button to tell me that I can pause this process if I want to. And now the line has changed to show me the real voltage that the device reads here in real time and the watt-hour capacity based on the moment that I started this test all the way to the present moment. Okay, this watt-hour number gets to be updated every minute, so it takes a minute to add something more. And this process, you will see in a moment that you know, the watt-hour value will change. This process will basically keep on going until this voltage reaches that threshold that we have set earlier, which was 3 volts. When that will happen, the process will stop. I will show you in a moment, and will tell us the final capacity in watts hour. Okay, so you can see now that this number has changed from complete zero to 0.028. and it will keep on going up. Now, while the process is running, we can, if we want to, we can see the actual current that this device is drawing. If we go with the select button, we go with the cursor to the watt hour rating and we press the action button. Okay, now the device shows us the real current that he's drawing. We told him to draw 420 milliamps and we see that he is drawing 427, 428, depending on the case. If we want to go back to watt hour, we can click another time on this and we'll change back to watt hours. Okay, regardless of where we are, like I said, this process will keep on going until the voltage drops to that threshold. And I will do so right now. I will lower the voltage from my power supply. You can see that on the screen. And when the voltage has reached that threshold, the device stops sucking current from the accumulator and considers the process finished, completely finished. He will keep on displaying the last voltage that the accumulator had on the screen. He will put a check mark on the icon to basically show us that the process is finished. And he will display the watt hour rating at which he has arrived up until that point in time. And this is going to be the capacity of that accumulator. Okay, at this point we can, and he's gonna stop here and basically wait for us to come and to read these and to reset him. In order to reset him, we go to, with the select button with the cursor to the icon and we press action again. And now everything has reset and we can start all over. We can change the current if we want, we can change the voltage and so on and so forth. Okay, this is how the device works. This is how I created the software to work and to be able to display and control everything with just 16 characters on 2 lines of LCD screen. So yeah, I would say it's pretty nice. Overall, I am content with this device. Make sure that those Darlington transistors are placed on proper radiators. I have them here. Each radiator is, mounted with 2 screws. Those transistors need to be cooled down properly. Otherwise, they will they will burn at some point. Especially if you decide to draw higher currents, more than 1 amp. Even at 1 amp, they need to be placed on cooling radiators. But especially if you draw more than 1 amp from your accumulators. So yeah, so that's pretty much it. Like I said, I will put on Patreon for all the paid members all the necessary files for you to download, get the software, get the schematics. I just need a couple more days to set everything right, and I will put an archive over there. And I hope you enjoy this project. It's definitely, for me, it's definitely going to be useful. I've already done some tests with 16 pretty cheap accumulators, and I will buy even more that are going to be even cheaper, and I'm really curious to see how small their capacity is. So yeah, a new video is definitely gonna come pretty soon on this channel around this topic of unknown litiu accumulators that we want to use. So thanks a lot for watching this project, this video. A like and subscribe is free and helps the YouTube algorithm spread the word more. Perhaps other people are interested in my work. Thanks again, and I will see you soon in the next video. Bye bye.